So third lesson is on approximations, linear approximations, or using tangent lines to approximate tough function values that you can't do by hand. So we'll start by doing this little activity. We're going to find the equation of the line tangent to f of x equals x to the 2/3 when x is 8. So go do that. Remember, for a tangent line, we need our tangent slope. And we'll need our point. And all together, we'll put that in our y minus y1 equals m times x minus x1 point slope formula. What I handed out to you is your homework. It is a worksheet. There are no questions like these in your book, so you have a worksheet. So tangent slope I'll get from my derivative. Let's make sure we can find our derivatives correctly. This would be 2/3 x to the negative 1/3. And then I'll plug in 8. 2/3 times 8 to the 1/3. Well, the cubed root of 8 is 2, so this is 2/6, which is 1/3. Okay, then for my point that I'm going to use, I will plug in 8 into my original function. F of 8 is equal to 8 to the 2/3. Now, what is 8 to the 2/3? Good. We know that because this is 8 to the 1/3 squared. We have a power to a power. And the cubed root of 8 is 2, squared is 4. So we got the point 8,4, y minus 4 is equal to my slope 1/3 times x minus x1. All right, so that's my tangent line. Well, I'm going to go ahead and graph. I have x to the 2/3, it looks like this. And I'm going to graph the tangent equation, 1/3 x minus 8 plus 4. I won't even bother distributing. I'll just say it's 1/3 quantity x minus 8 plus 4. So let's go into Zoom Standard. This is what x to the 2/3 looks like. And now here's my tangent equation at the point 8, 4. Okay, so it looks something like, I don't know, this, right? Well, I'm going to zoom in around this point 8, 4. I'm going to take this and I'm going to zoom in right there. And there's x to the 2/3. And there is my tangent equation. So zoomed in, it looks like this, and then kind of like that. Well, What do we notice about my function and its tangent equation when I zoom in around the point 8,4? Yeah, it's pretty much the same. And we will use this fact to help us approximate function values of x to the 2/3. Since I know that this equation will mimic my function around the point 8,4, I can use this equation and I can plug in x's to produce approximations for f of x. If I plug in x's, I'll get y's. But what are the y's? The y's will be approximations of my original function. Of course, the x's I'm going to plug in are going to be close to 8. Because if I want to approximate like f of -1, I'm not going to use the tangent line at 8,4. It doesn't make sense. It's only going to be points like right here and right here that aren't easily done by hand, but I will be able to by hand find the approximations, and those will be, you know, pretty close values to what I'm actually looking for. So let's do that. Let's figure this out. I have this function x to the 2/3. That's what we're kind of focusing on to start. And I want to figure out what f of 8.1 is. I want to figure out what 8.1 to the 2/3 is. Well, I'm not going to try to take the cube root of 8.1. Sure, it's going to be something close to 2. But then I square it and like, sure, it's going to be, you know, something around 4. But let's get a really, really good approximation for this. Let's get like accuracy here. So instead of just like guessing, instead, I'm going to use this tangent line equation at 8,4 to generate this point at 8.1. So I got y minus 4 is equal to 1/3 x minus 8. Well, to figure out y's, I'll plug in the x of 8.1. Get y minus 4 is equal to 1/3 and 8.1 minus 8. Notice I didn't solve for y. It's actually going to be easier if you plug in x while it's still in parentheses, because this will be an easy decimal to work with. Get y minus 4 is equal to 1/3. This is 0.1. Now, 0.1, if this was like 3, I would just multiply 3 by 0.1 to get 0.3. But this is 0.3 repeated, so instead I'll treat this as 1/10. And if I multiply these two together, I'll get 1/30. And then to figure out this y value, I add 4. So adding 4 to 1/30th will be like adding 120 over 130, or 120 over 30, to give me 121 over 30. So using the tangent equation to x equals 2 to x to the 2/3 around this point 8,4, I'm going to say that 8.1 to the 2/3 is approximately, can't speak today, 121 over 30. Well, let's go ahead and check to see if that's correct. So 8.1 to the 2/3 is exactly 4.033264.272. Let's see, 121 over 30. 4.033. Not bad at all. Okay? This is all done by hand and producing a very, very accurate approximation. Something that I couldn't have done just by guessing. Well, you guys try. Let's just go, like, we could do the same thing for 7.9, 8.5, 8.01. It's just using the same thing. But the important thing is to be able to produce this tangent equation and then plug in the value that you want to get your approximation. Okay? That's the procedure. We just did it for 8.1. We found that it was a pretty good approximation. Let's do another one. So I'm giving you a function, x to the 5th plus 2x. I want you to approximate f at 1.1 and f at 1.01. Well, I'm also going to tell you that f of 1 is 3, that it's telling you where to focus your attention around the point 1,3. So I want you guys to go ahead and try to find approximations for these two values. I don't know what 1.1 to the 5th is. That's going to be tough to do. So I'm not going to do it. Instead, I'm going to approximate. So produce your tangent line. Around the points where you're trying to approximate. So I'll produce a tangent line at x equals 1. And then once I produce my tangent line, I'll plug in 1.1 to get my approximation, which will be the y value. Now, instead of putting this as 7/10 and having to deal with fractions, 0.1 times 7 is just 0.7. I add 3 to 0.7, I get 3.7. I think 1.1 to the 5th plus 2 times 1.1 is approximately 3.7. How do we do? Close. Not bad. Decent. Well, what about f of 1.01? Would I get a better approximation for this? Mr. Jesperson, you nodding your head yes, and why? Yeah, closer to the actual point, the tangent line will be mimicking your function even more. So even though this was off a little bit, let's check f at 1.01. .07. Ah, that's better. 3.07. Thanks. Well, we can use these tangent lines to approximate square roots of numbers that are not easy to do, like the square root of 17. I don't know what the square root of 17 is. I know that it's a little bit bigger than 4. I know that it's going to be less than 5, but let's get a good approximation. Well, let's go ahead and do this. Let's try to approximate the square root of 17 using your function, the square root of x, and knowing that the square root of 16 is 4. So develop your tangent line when x is 16 and use that to approximate f of 17. Four and an eighth, that's 32 eighths, right? Which is 33 eighths. Have to use a fraction here because I don't know. Well, 1/8 is not a, well, it is a finite decimal, 0.125, right? Yeah, so 4.125. Well, let's see. Square root of 17, 4.125, 4.123 is the actual answer. You know, accurate to the 100th decimal place. Not bad. Decent. Okay, well, not only can we talk about being, you know, pretty close approximations to functions at certain points, but we could also say, hey, this approximation that I gave you, that's going to be just over your real value. Or, hey, this approximation that I just gave you, that's going to be just under your real value. Here are two curves, and I got a black point, which is on my function. Say this is at like 4.2 or 4.6 or something. And say this red point is at 4.1. Say here it's the 0.26, and this is 2.1. And I'm trying to approximate that red point at 4.1 and 2.1. And I'm going to use the tangent line at this 0.46 and this 0.26. Scales are different, of course. The question is, when using these tangent lines, which one will produce an over approximation and which one will produce an under approximation? Think about that, everybody.
The one on the right be equal to approximation?
Let's think about it. Is the one on the right an over approximation and the one on the left then an under approximation? Well, if I drew my tangent line, let's do that in black maybe. This would be the tangent line that I would use to approximate this point in red. The tangent line would produce this value here. This value is under the actual value. So yes, this is an under approximation. And over here, my tangent line would end up producing values at 2.1 that would be above my actual value. So this is an over approximation. What's the difference between the two graphs? Exactly. It's not the second derivative is positive, the second derivative is negative. The difference in these two are the concavities. This graph is concave up, and this graph is concave down. So, if I know what's going on with my function, if I can produce a tangent line at a point, and if I know the concavity of my function, I not only will be able to produce a decent approximation, I will also be able to say, hey, that's an approximation, and it's going to be over or under my specific value. So let's look at this guy. There's a function, x cubed plus 4. I want you to estimate that function at 2.01, knowing that f of 2 is 12. And I want you to tell me if the approximation that you produce is going to be over or under my actual value. So I get my approximation is 12.12. Now is that an over or an under approximation? Under. How do we know it's under? Because f double prime, which is, I'll put it over here, f double prime is 6x, and f double prime at 12 is, and really just everywhere around this, is positive. So you're thinking, okay, that means f is concave up around 212. I always, even to this day, I always have to draw a piece of a graph that's concave up. And I always have to kind of sketch my tangent line just so I can think about it. And I say, okay, the tangent line is under my actual function. This, which is my approximation, is an under approximation. This is under the true value of f of 2.01. Why don't we check? 2.01 cubed plus 4. $12.1206. Wow. Just under. But it's under. It's under. How much under? 0.0006 under, Miss El Haj. Isn't that unbelievable? Wow. That's exciting, right? Gosh. This is exciting. It's exciting. Okay. Another question. I'm just not even going to give you the equation. I'm just going to give you information about G. Now there's just points. And we're too many 5s here. This is 3. Okay? I want you to find the approximation for G of 4.9, and I want you to tell me if this approximation, an over and under approximation. What's great is that they give you all the information to produce your tangent line. So I get G of 4.9 is approximately 2.8. Over or under? I heard of a couple things. Let's think. G double prime is less than 0, so that means we are concave down. Here's a piece of graph that is concave down. Here's a point, and here's a tangent line. Now, what's great is that it does not matter where this point is. This point could be to the left or to the right of the point where my tangent line is, no matter which way it is. In this case, we're talking about 4.9, which is to the left of 5. The tangent line is still going to be above your actual function value. So this is an over approximation again. Yes?
Do all that work when you know it's concave down? Draw it and say, okay, it's over. It's just giving us a
Yeah, I just want to make sure you can see that that's an over.
We'll ask for what.
Well, I want you to find the approximation of G of 4.9, and then tell me if it's an over or an under. Okay. Cool. We can use a derivative equation to approximate a 0. So say I have some function that looks like this. And say I don't know where a 0 is located, but say I know at like 2 I have the point 1, and then at 3 I have the point -1. Well, I know that somewhere in between we're going to cross. Well, I can actually think about connecting these 2 points and figuring out the line of this line that connects those 2 points, and I can use that to kind of estimate where we're going to cross the x-axis. Or I could just use the tangent line to one of these points and kind of use that to estimate where we're going to cross the x-axis. Okay, so if I know that f of 3 is 5 and f prime of 3 is 2, I can approximate a location of a 0, so that's the location when a y is 0. You know, it's probably better if you know the point on the left and the point on the right and connect them. And then even though there's like a little bit of concavity, maybe concave down or concave up, a straight line would do a good job approximating. But right now we're just given a point and a slope at that point. And if I want to approximate a 0, plug in 0 for y, I find x. That's it. That's one thing. If I give you 2 points, develop the line between those 2 points, and then once you have the line, plug in 0 for y. This is an AP question from a previous year. Let f be a function that is differentiable for all real numbers. That means that you can take the derivative, that's all. If it's twice differentiable, that means you can take the derivative twice, that's all. Table above gives the values of f and its derivative of f prime. I'm hiding the derivatives of f prime for a reason. The second derivative of f has the property that the second derivative is positive for all x's in this interval. Write an equation of the line tangent to the graph of f at the point where x is 1. Use this line to approximate the value of f of 1.2. Is this approximation greater than or less than the actual value of f of 1.2? So many words on these AP problems. Okay, well, I know that f of 1 is -4. Right? But I purposely hidden f prime of 1. But I need the slope of the tangent of f at 1 to create a tangent line. What should I do? Right? That would help. Which was what? I still need f prime to figure that out. So no, not going to do what I did on the homework. Yes, Mr. Kaiser has got it right. We don't know what f prime of 1 is, but we can approximate it. How do I approximate it? I can use maybe 1.5 and 0.5 I can use maybe 1 and 1.5, 1 and 0.5. Let's just use 1.5 and 0.5. So the slope of the secant will give me a decent approximation of the slope of the tangent. This is 5 over 1, that's 5. So y plus 4, is that right, 5? Yep. Equals my approximate slope 5, x minus 1. And then I approximate 1.2. Point 0.5 times 0.2 is 0.1.
What's the 0.5?
Oh, I don't know where the pi is. Back. Five times 0.2 is just 1. -3. And over or under? Concave up. Under. All right, congrats. We got 5 minutes to either start our homework. I know. Or you can relax. Yeah.